Hi, good morning, everybody. Damodharan is here to give a talk on for the session.
Yeah, thanks a lot for the introduction. I'm Damodharan working in Zoho. Today we'll be looking at JSON schema and how it can be used as a runtime type system. So right now I'll start sharing my screen and getting started with the presentation. The thing is that type system always tend to be at compile times, right? There is a unique situation where we might need type system at the runtime too. And this in case JSON schema seems to be a perfect fit. Let's look at the introduction of JSON schema. Typically, as software engineers, my almost daytime job is to transport JSON from one place to another. And always there needs to be a validation to be set up at every part of the stack, right from the front end to the database to the back end. And right now, AI is also a part of the stack, right? LLMs and so on. Where we get the JSON from and where it is going to, there always needs to be some kind of validation, and this is where JSON schema comes into play. Let's look at the basic primitives that are present in the JSON schema. Very typical of other programming languages, JSON schema also has access to primitives and then its constraints. Let's look at what a basic string in JSON schema looks like. So this is a playground for validating a JSON schema. You can have your schema over here and the output over here, and this will tell whether this particular output is valid against the schema that we are writing over here. So let's say this is the JSON schema for the primitive string. So what it says is that the schema, the value that is given for this schema is right. JSON schema is kind of a constraining system where you start with an absolute basic of just the string, and it gets and you can keep adding constraints on top of them. For the number, it is just again very similar to how we write the string. So this number one gets validated. Let's say I give a string instead of number, the schema gets invalidated. So the thing is that you can start adding constraints on top of this basic primitives too. So what we can do is that we can say max length is 5, and then let's say we start adding strings to it. The moment I add the sixth character, the schema gets invalidated. So this is very typical of liquid Haskell, right? Liquid Haskell has this constraints on top of your basic types where you can keep adding more, and then you can keep getting more validated data types. So other kind of validation that you can do in JSON schema are array and then object too. So let's look at how we can constrain arrays. So basically what you say is that the data type is array, and then the individual item inside the array is going to be a number. So this just gets validated, right? So we have an array of numbers, and then this just get validated, and you can type the what items have to be inside the array too. So if I just say string over here, now it gets invalidated, and the moment I add string over here, the schema is gets validated again. So this is very reminiscent of again objects too. So objects are to be defined in JSON schema like this, where you say what is my key, and the type of the key is going to be this, and then another key that is over here. And since this is a constraining system, an object can have additional properties along with name and age also. So we just say that additional properties shouldn't come inside this. Just as we say in a class or an interface, it always matches against whatever we define over here. But in this case, what happens is that by default it allows additional properties, and we have to say like additional properties shouldn't be coming over here. And since an object can also be optional, the name can become optional and age can become optional, but we constrain them again saying that definitely this has to get name and age compulsorily. So now let's look at this object that we are given here, and it says that it is matching the schema. So as a regular JSON, if we give any other key over here, it gets invalidated again. So this is how you constrain objects in JSON schema. Continuing, so this isn't just a type system, right? What we have seen till now are just primitives and then collections, which is very reminiscent of any programming language or any language with a weaker type system. But let's say suppose we go for an additional constraints. So that is what the connectives come into play. Let's look at all of present in JSON schema. As we have seen already, what all of does is that it is equivalent to the AND operation at the type level. So what happens over here? I say the type is going to be string and the max length is going to be 5. So both have to get satisfied in order for the schema to be valid. This case, it's get validated for the max length of 5. And moment I add something, it goes, yeah, the schema validation error happens. So let's say, suppose you have additional constraints over here, you can keep adding them over here, and then it gets validated against whatever you give over here. So the next that we are going to see is any of. So what any of is that it is similar to OR operation. So so here we have an example which says it can either be a string of max length 5 or it can be a number of minimum 0. So here I give -1 where it says that minimum has to be greater than 0. So the moment I turn into 0, it gets right. And also it can be a string of max length 5 right again. So I give till 5, it gets validated. The moment I give the 6th character, it gets invalidated again. So this will be very useful, and we are going. So let's look at another connective that is very reminiscent of types in other strongly typed languages. So now let's look at this one. So what one of does is that I have again very similar use case to the previous example. It has an object and this also has an object. The first one accepts a circle and the second one accepts a square. So what is the difference between any of and one of is that any of is reminiscent of or, which is like whenever it has the first match, immediately it gives you the output. But one of what it does is that it keeps matching for every single match that is present inside this one, and then it gives you the best match I mean like the last match that is over here. So in this case, this is very reminiscent of discriminated unions or the some types present in the programming languages. So this can be very much compared with that one. So in this case, what we have over here, circle and the radius, which has to be number. And let's say I turn this into a square. Now square should always have a side length, which is the number instead of radius, right? So the moment I give the side length over here, the schema gets validated. So it has to be either a circle or the square, nothing more or nothing less. And everything else is the same as the previous ones, required and then so on. So, as we have seen, started from the primitives, collections, and then the connectives. The next obvious question in a type system is that whether reference is possible for the case of recursion. So this is what we usually think. We want to model a linked list or a tree or something. So we need to reference the object itself. That is the example that we are going to see right now, which is actually a tree. So what we have over here is that an object whose value is going to be just the number, and we have, this is a binary tree where you have the left and the right, and the left can either be null or it can refer to the node itself. This is the tree node. So this is the keyword that we use in JSON schema, $reference, where you can refer to the entire object itself. So the left attribute can have the entire thing, and the right is also of a same definition. It can be either null or it can be the entire thing. So there is no reference to the name tree node, right? So how this we can give a name to this schema is that you just have to use a $ID, which is very similar to HTML ID that we have, right, for referencing each and every node with a unique name. So the moment I give this schema a name, it can be referenced using this $reference, which is like during the validation of the schema time itself, it will get replaced, very similar to that of a macro or something. So now as we look at the example, we have this value and the left is going to be null and the right is going to be again a tree itself. Let's see whether it is validating against it. Yes, it gets validated against perfectly. And if I don't give a left value or something, again it is not going to get validated correctly. So this is how we do recursion and self-reference within JSON schema. So right now, I think we have everything in the plate in order for a JSON schema to be used as a type system. So now let's look at an algebraic data type definition in JSON schema, just like we do in any other typed language. So we just saw the definition of the tree, right, with the reference of referencing itself. So, but the point is that it is very, let's say, very static tree. You just say it is just the value should always be a string or something, but that isn't enough for us, right? We need a generic tree actually. So, how do we do a generic tree in JSON schema is that we need something similar to the generic types present in the functional programming languages. We need some like tree of string or tree of number that has to get replaced at the runtime of using the data type itself. So let's look at the example of how this is done. So this is achieved in JSON schema using a feature called as dynamic reference. So what dynamic reference does is that it gives you the full control of the generics that is present in the functional programming languages. So let me introduce like one more feature of the JSON schema, which is actually called as $defs. What $defs does is that it gives you a series of definitions that you can use in your schema. So these are all the definitions that I have over here, but I just use list. That's it. Nothing else I'm using. So in this entire schema, all I'm using is this list alone. Now let's look at the definition of the list. The list has an ID and it's going to be an object, and its value, instead of directly saying it as a type string or type number or something like that, I'm just saying it as dynamic reference of t. This is very reminiscent of list of t. Let me just open my Visual Studio Code. I'm just writing my Typescript over here. It can either be null or it can be another list, right? So let's say this is what we are trying to achieve, t or list of t. This t is what we are trying to define over here. So where will I get the value of t when I'm using the list? So what we can do is that the list alone is getting abstracted away without the t. The t can be defined inside the definition where I can see this t will take number, and this is getting validated against. For this validation, we are using a library called as hyperjump, where it says this is correct. Now, in order to make a linked list of string instead of number, I just have to change over here. But the definition of the list does not get affected at all. Now, if I validate against, it says it's wrong. The moment I turn this into string, now this is getting validated. So this is how we achieve generics that is present in functional languages within JSON schema. And this is how we can achieve generic maps, generic tree, and then so on. And I have multiple validation libraries because certain libraries don't have certain functions, and the spec of the JSON schema keeps changing every year, and in order to stay updated, like the validation library has to follow up through the spec, and it is better we always look forward to using new specification without breaking our existing code base. So moving further, we have like even stronger validations present for JSON schema, which is similar to dependent types actually. So a very basic example that we usually come across during our development is that there can be some properties within an object which will be dependent on other properties, right? So which is like similar to let's say this object, it has payment and then card number, and then this payment is always dependent on card number. So let's look at the example of how this works. Here in this one, what example we have is that we have name, credit card, and billing address, and name is always going to be required. But in order to have a credit card, billing address is its dependency. So let's say in this object, name and credit card, I remove my billing address. Now it doesn't get validated, right? So, but billing address alone can exist. So this gives us a kind of dependent type kind of behavior where one property is dependent on another. So this is how we achieve this in JSON schema. But is it just enough? but because like we need conditional schemas, right? Certain places you need to have complete if and then cases, and that is what happens over here. Say you have this particular thing where you are in this property, you have a street address and then country, but the country is an enumeration. Just as we saw some types, this is a shorthand for enumeration. It can just have, the country can have either United States of America or Canada alone. But here comes the interesting thing. When the country is going to be the constant value of United States of America, then the postal code has to follow a certain pattern. So again, we are making use of the previous learnings from it. In spite of this being just a string, we are also adding a refinement on top of it. We are saying like it should follow this pattern. Now this is getting validated against perfectly for United States of America. But the moment I change this to Canada, it says it doesn't match because it has to come under the else case, because the country is no longer United States of America and the postal code of Canada is going to be different. It has to start, the pattern has to be something like this. So what does it start with? It's a regular expression given a capital letter followed by a number, a capital letter followed by a space, number, capital letter, and then a number again. Now this is correct. So this is actually dependent on the runtime data, the whatever this is coming in. So very reminiscent of dependent types present in some functional languages. Not exactly like provable kind of dependent types, but very close, structural dependency. And another good thing is that instead of directly, even before this feature came into the JSON schema, people were able to use this. And this is a very nice kind of hack, because if then else can always be represented in logic as P implies Q, or not P or Q, right? So not P or Q is always like if P then Q. So how do we represent not in JSON schema? So this is the usual. The object has restaurant type, total, and then tip, and then so on. And this is going to be an enumeration of these two strings. And this is where the interesting part comes in. Any of. So we use any of. It can either be this or this. It's going to be not P or this Q, right? So what this actually says is that if the restaurant type is going to be sit down, then definitely tip has to be given. If it is fast food, then there is no problem. But the moment I change this to sit down and it says tip is missing, so we need to definitely add this tip. So even without if then else, we are able to achieve this behavior within JSON schema. But since if then else is kind of a syntactical sugar, it is better to go with that one, and it is easier to read because this isn't obvious. So this kind of gives us a flavor of type systems and its behavior, right? So we usually have this correspondence and so on, like how do we relate from logic and then stuff. So this behavior within JSON schema was like very interesting. So moving further, this tool that I was showing you, this was written using a JSON schema validation library called as AJV in JS actually. So this library is kind of a go-to place in the TypeScript environment, where we can define schemas and then validate it against the given structures. So one more interesting thing is that this particular library lets you extend the JSON schema library itself. Let's look at how this is being done. We just saw the example of list, tree, and what if we want to model a graph. So let's take this example graph, and it has 3 nodes and then 2 edges, right? And then this is the JSON that models this particular graph data structure. But the validation in this one is that the source and the target should always contain the IDs present over here. It has to be either 1 or 2 or 3. Let's say if I give target as 4 over here, it won't the schema should throw you an error, so it shouldn't like accept this JSON. So how do we define a schema for such a structure that is not present in the JSON schema base specification itself? That is where defining custom vocabulary within the validation library comes in. So let's look at the base schema for this particular graph. All we say is that we have nodes and then edges, and both are going to be array. And then node has to have its ID and label, and the edge has to have a source and target. That's it. So this is all the structure required for the graph. But the key validation is not present, right? So what we do is that we define a specific, a very our customized vocabulary called as check node ID, which is getting used in the schema. So what we do is that whenever this check node ID comes inside the schema, we write a validation function which checks for the nodes inside node IDs that are present in the root schema, and it says whether it is present or not. That is all the validation function we write over here. So this gets registered in the AJV as a new keyword. And then now let's see how the modified schema is going to come in. So we just make one small change. What we do is that inside the edges array, we say whether the check node ID is true or not. So whenever the source gets a particular string, this function gets called and checks whether the ID is present in the node array or not. So this one, let's say for this example, I have ID 1 and 2, and then I say edge is connected to 1 and 3. There is no such thing as 3. And immediately the JSON schema library will start throwing you an error. And this way, you can extend your JSON schema to like validate even more validate additional data structures that are not reminently like usually present in the base specification. So this lets you add custom business logic and then so on, which is kind of useful. And another ecosystem, good ecosystem player is that Faker. What Faker does is that it takes a JSON schema and gives you examples. It gives you like fake data for this one. And this is very useful in testing our testing and then mocks. Let's say we are waiting for the backend and then it is not yet present. We can immediately get started with define the schema so that it acts as a contract between the front end and the back end, and immediately we can have some kind of a fake data so that we can start working on the back end. And then the same thing can happen in the back end also. The same schema can be used in the back end so that the front end and back end is always in sync till the development is kind of done. This is kind of useful for such scenarios. So going back to like the root cause of this talk, for the previous functional conference, I gave a talk on TypeScript actually, and many of these ideas were happening within the TypeScript. And the TypeScript ecosystem is that it always the types always reside in the compile time actually. So what if we want to take it to the runtime? That was one of the questions during the previous talk, and it was also bugging me, right? So every time you define a TypeScript type, you'll have to again like do the validation manually. So JSON schema is actually kind of a runtime type system that kind of complements TypeScript in a very great way. So again, we kind of end up in a scenario where you define the compile time types. You again define the runtime types using JSON schema, which makes the type definition twice. So how we can have a single source of truth so that that can be used in both compile time as well as runtime, and then go ahead with the development. That is where this particular library comes in, Typebox. So this is kind of a very highly used library. So what it does is that we just have one definition of this type. We define what this says is that we define a type which is an object. Let's say open is the key. The value has to be a literal of testing, and then testing has a value of closed, and closed has a value of open. So this is the structure that the library gives for you to define the type. Now we need the compile time type as well as the runtime type. So how do we achieve this? This one is the compile time type, and this one is the actual runtime that we get used. So it gives you a compiled type operator that can extract the type from this definition. So whenever I hover on this, the editor immediately finds out in TypeScript that it has a type of this one. And in this this particular API from this library, what it allows you to do is that it works similar to faker.js. It gives you an example of the type that is being defined in the runtime itself. So this is creating an example of this one. And if I hover it, it immediately is able to say, okay, this is the kind of runtime type that I'm able to get. So we kind of achieve something similar, right? So this is kind of there. Again, so we have all of the type operators that are present in the compile time available at the runtime also. This is like taking the entire, this is kind of a wrapper in TypeScript on top, TypeScript written on top of JSON schema that is available as an API itself during the runtime. So let's look at what other operators it is able to give. I can say what are the keys present in this particular object, and it immediately says it has open, testing, and so on within just a hover of the thing itself. And this is also available during the compile time again. So you can easily switch between compile time and runtime definitions with this library, which is kind of like crazy and then very useful at the same time. So what I'm doing over here is that I'm trying to define a function which takes key of this one and returns this particular value. And all it does is that it just gives returns it back. And if I do an implementation of it and then hover on top, again it is able to give me what are all the possible output types of this particular thing, which is going to be open, testing, and then closed, which is kind of crazy. So like this is kind of traveling between the two places, right? You have a single definition of the type, you go to the compile time, runtime, again compile time and runtime, and so on, depending on your use case. This was like a very good showcase of how JSON schema helps you within both the worlds of the compile time and runtime within the TypeScript environment. So moving ahead, LLM has become a part of a stack itself right now. Like every single business trying to integrate AI into their stack. So one of the basic cases is that it always gives you some kind of a markdown where you have a bunch of natural language text followed by a particular fencing of code, or again followed by a bunch of text. You need to know where the proper code is always coming in. When it comes to like developing actual applications, the language model has to give you proper JSON, right? It has to give you proper JSON every time in order for us to process and then show it on the front end or back end or something. So how do we usually go about this is that we say give me JSON as an output in the prompt, but does it always guarantee JSON? That is always a doubtful question, right? We always have this problem of whether it will give me a proper JSON or not. It does in the most of the cases. Like OpenAI just came up with a specification with a particular feature called as JSON mode, where you say the output is going to be JSON mode and it tries. But even in their documentation, JSON mode says something like the kind of accuracy is very less. And this is where the open source community came up with a very good idea with respect to JSON schema and then programming language theory, which is kind of very interesting. So what they did was that they given a JSON schema as an input to the LLM along with the prompt. It should always follow this schema and then give me the JSON as output. But how does a non-deterministic LLM does it? So let's look at the demo first. Here I'm asking it a question of what is 2 plus 2? And then this is the schema that I have over here. So what I'm saying is that it has to have steps followed by a final result, where steps is an array which has description and then result for each step, and the final result has to have just the description alone. And the question I'm asking is what is 2 plus 2 star something, and then let's say divided by something or so. So now let's have the structured output from this. So it has given me a particular answer, and it is of perfect JSON. And this is actually coming from OpenAI, and this is not JSON mode. So this is using actually structured outputs. So when I'm formatting this JSON, let's look at the structure that it has given me. So the first step is that it is able to identify it as a mathematical expression. and according to the expression, and it does something. And at last, it is doing all the step by step, and then the final result has been given. So now this is a very useful format that we can easily consume in the software stack, right? This always returns you a perfect JSON. So this is kind of very useful for our usual consumption. So how does it actually do it? So what happens is that whenever a schema is given, the schema is getting parsed, and it is converted into a grammar rules actually. So this grammar rule is then given to an EBNF grammar, and then it is just compiled to get an optimized grammar. So now actually what happens is that whenever there is a user prompt, the next token that is getting generated, it is not just generated from the prompt alone. It also consults the library. The inference time of the LLM actually does it. And the unique thing about this case is that open source LLMs were ahead of this particular thing, and they launched it. So Illama.cpp is one of the inference libraries that actually runs in our local hardware itself. And then when I was trying it out, I had this unique case where I had to translate a particular JSON objects right side keys alone into like Indic language Tamil. So I gave this particular thing in the user query where the keys were in English, and the LLM was able to give me just the JSON alone. The assistant was able to give me the JSON alone, where the value was alone in the required value was alone in Tamil. So it was kind of very easy to do it. And then this isn't OpenAI. This was running in my local hardware with Google's Gemma, which was like very good at translation and then instruction following too. So it is kind of crazy, right? So let's look at one of the libraries, like how they actually do it, with a kind of small demonstration over here. So in this particular thing, if this is the JSON out that we are getting from the LLM, the brace, this temperature, until the colon, we don't need the help of LLM itself in order to get the out. So these entire tokens are completely generated by the grammar that has been compiled from the JSON schema. And this 24 alone is where the LLM is getting consulted. And this way, the structured output is kind of constraining the LLM to always give us the perfect structure. So there has been like multiple researches going on, like does it like constrain the LLM from giving us the correct answers or not? But multiple benchmarks have shown time and time again that structure generation, and especially with respect to JSON, LLMs are very good at giving the perfect answer. So this is kind of very path-breaking with respect to it. So this is the thing. So what other things can be of future directions with respect to JSON schema is that we have this particular various validators present for JSON schema, right? So in this one, we have AJV and then hyperjump, these validators. And since the schema is of dynamic nature, so schema can itself be sent dynamic nature in dynamically in a request, so that it can be called in the front end, back end, and so on. So all we need to do is that just use the library. But what if the schema gets more complex? And what if sometimes the schema is also static? That is where the compiler for JSON schema comes into play. And this is again from Typebox itself. So what Typebox gives us is a type compiler which gives you a high performance JIT validation library. So let's say I have a particular schema over here, and I use the type compiler for it, and it gives you a JIT compiled version of this particular validation, and this validation is like way ahead in the speed compared to the normal AJV library also. We can always use this in case of static schemas. This is like kind of very fast. And another important takeaway is that next token prediction, as we always tend to look at in LLMs, what the next token prediction, The one next token predictions that we have been using for a very long time, even before LLMs, is that the language server protocol in our IDE, right? So let's take some kind of an IDE, and I write this, and the moment I hit dot, it gives me what is the next that has to come over here. So this is defined using the language server protocol for every language, and various IDEs are able to catch this up and then like give you the next token prediction. So why not just constrain? Why not just like open this up for the LLMs too? So given the work that has already been done, as I showed you in this case, this is getting constrained within JSON schema or the grammar alone. But what if we open this up? Open this up in the case the next token prediction within this within the LLM need not be just the grammar alone. It can be a regular expression. It can be your customized logic itself, the sampling logic. So let's say these are the previous tokens that I have. Whether the next has to come from the grammar or the LLM or something else. So the moment this comes in, we have a very generic sampler where we can tame the outputs of the LLM even more. And so since JSON schema is kind of going to play a very big role in this, we kind of need an LSP for the JSON schema itself, and the JSON schema specification team has been working within the editors too. Let's say I keep using JSON schema within the editor, what has to come next? Like we need the editor tools that are present in the various languages to be in par with the JSON schema also. Now coming back to the last one, so we already had a look at AJV library for validating JSON schema, right? So they have this keyword called as $merge and $patch. So this kind of is interesting. So let's say you already have a schema, and then you want to merge it with an existing schema. You just try to compose, very similar to the compositions present in functional languages, but this is kind of structural compose and the constrained compose. Like it has this customized keyword that is not present in the usual schema called as $merge, where it is able to combine these two and give you this equivalent object. So what it does, P is over here, Q is over here, and it combines and gives you an this object. So this can keep adding up, right? P and then Q and so on, and some things can be in dynamic and then stuff. So what if this particular merge is very reminiscent of actually having an interpreter, right? So I have this instruction followed by this instruction, and then it gives me this one. It kind of reduces. So whenever there is a reduction, then it is actually an interpreter itself. So this does not have to be in the merge structure. It can also be in a patch structure too. So what does this patch do? So patch does is that it has a key called as operation, which is actually an add. On top of this particular object, I'm adding a property called as q, which is going to be number. So this operation, it need not be just one thing, right? It can be an array of things, and all the operations can keep adding on top. This is very similar to diffing of JSON. So these diffs can be a very huge array, and it can get interpreted and then it can get added. So it is kind of adding a logical layer in the JSON schema itself, which is like pushing the limits of JSON schema further. So this is still in the exploratory phase, and this can be like this can open up even more dynamic and logical things that can be done on top of JSON schema. So I think with this, my presentation is kind of done, and I think we can move over to questions or discussion and so on. Yeah, thank you.
Thank you so much, Damodharan. It was wonderful talk, and I mean, really enriching to understand the JSON schema landscape.